Welcome to Chapter 2, Atoms, Molecules, and Life. This chapter is largely about the first level of organization, that is atoms. So we talked about in Chapter 1 that you would start with atoms, and then atoms can combine to form molecules, and then molecules can combine to form cells. So the combinations and structures of molecules and atoms determine much of the functions of cells. And in this course, we will largely be talking about things that happen in cells. So firstly, what is an atom? Atoms are the fundamental structural units of matter and are composed of three types of particles. An atom cannot be divided into anything smaller than an atom other than in a nuclear fission bomb. So no chemical means can make an atom into anything smaller. So it's the fundamental unit. Three particles. In the central nucleus, there are positively charged protons and uncharged neutrons. They both have mass. We say that they both weigh 1. And sometimes we'll say 1 AMU, or atomic mass unit. But that's a little bit more chemistry than we're really going to be getting into. But they have mass. Sort of in orbit. We say orbit because this isn't, again, a physics or chemistry class. Orbit isn't quite the right word, but in orbit around the nucleus are negatively charged particles called electrons. So let's look at this diagram down here. This is a hydrogen. Hydrogen just has one proton that has a positive charge in its nucleus here, and then one electron that is around it. We say orbiting around it. A little more accurate would be maybe kind of like a fly buzzing around a piece of food. It's sort of a chaotic pattern. There is an order to the way electrons move, but it's not quite like an orbit. It's not like the Earth going around the sun. Over here, this is the second smallest atom. So hydrogen is the smallest atom that there is. You can't have less than one proton. That's it. When we move up to helium, then we have 1, 2 protons, and then 1, 2 neutrons. So the 2 protons each have a positive charge of 1, and the neutrons don't have any kind of charge. And essentially what they do is they provide stability to the nucleus. That is their function. And they also have some mass. So helium, we could see, let's see, 2 protons, 2 neutrons, and that means the whole mass would be 4 atomic mass units. Generally, the structure of an atom is basically going to be however many protons there are, there's going to be the same number of electrons. So protons and electrons is largely what we'll be talking about when we talk about atoms. Atoms and elements. So an element is a substance that can neither be separated into smaller substances nor converted into a different substance by any ordinary chemical reaction. Pardon me. Take hydrogen again. You cannot make hydrogen into anything else. Hydrogen is an element. It cannot be made into anything else by any ordinary chemical reactions. Now, obviously, you could take hydrogen, and let's take a look over here, if we can follow my cursor there. And if we combined hydrogen and oxygen, we could make water, 2 hydrogens and 1 oxygen, H2O. But we would still have the same elements. We'd still have hydrogen, and we would still have oxygen. So elements are all the types of atoms. Another way that generally an element can be defined is all elements, so hydrogens, they all have the same number of protons. All hydrogen atoms have 1 proton, and all oxygens have, how many is it? 1, 2, 3, 4, 5, 6, 7, 8. 8 protons are in oxygen. 8 protons are in oxygen. You do not need to memorize the number of protons in any of these. But all atoms of one element, same number of protons. Atoms and elements. The periodic table contains valuable information regarding each element, and you need to be able to read what all this stuff means. So number 1 at the top here, this for this element's ID card, this is what you would see. If you zoomed into the periodic table, you would see that each element has its own little square like this, and they all contain this information. So on the top is 1. That is its atomic number, or number of protons in the nucleus. So as I said, all hydrogen atoms have 1 proton in their nucleus. Next, we have an H, and that is the symbol for that element. And sometimes they start with the letter that you spell it with, like hydrogen. Oxygen is an O. Lithium is an Li, but sometimes they are not. And that's often because they were discovered in a language that is not English. Next, then we have the hydrogen, the name of the element, hydrogen, pretty self-explanatory. And then lastly, the atomic mass, or as is written here, the atomic weight. This is the sum of all protons and neutrons. And why is this not a whole number? I just told you that a proton has a mass of 1 atomic mass unit, right? We said 1 is just 1 proton and no neutrons. Down here it says 1.008. So why is it not a whole number? It seems like it should be a whole number. I will explain it now, but if it is confusing to you, don't worry. We'll come back to it in a minute. Some atoms of hydrogen do have a neutron, but that is rare. If you've ever heard of something like heavy water or a hydrogen bomb, for example, those atoms of hydrogen have a neutron, but they're really rare. So this number down here is actually an average of all the hydrogen atoms in nature. On average, it's about 1, but it's a little more than 1 because a few atoms of hydrogen out there also have a neutron in the nucleus. Next, table 2.1, common elements in living organisms. Really, just the first 4 are we going to talk about. Really, maybe more like the first 3. So oxygen is the most common, at least by percent weight. So we can see over here 65% weight in the human body. Why is that? You might have heard that carbon is sort of the backbone of life. In a science fiction movie, you might have heard that carbon-based life forms, we're looking for them, or the aliens refer to us as carbon-based life forms. Well, oxygen is more common because we are about 70-something% water, and water is mostly composed of oxygen by mass. Okay, so we've got oxygen, that's the most common by mass, and it's the most common because it's part of water. Carbon is the next most common, and that is because it is part of everything such as carbohydrates, fats, and protein. So it is part of all of those things. So it's really common. And then after that, we would get hydrogen. Hydrogen is also basically part of everything. And lastly, that I'm going to talk about is nitrogen. Nitrogen is part of proteins, part of amino acids. Proteins are, we could very simply say, part of meat, I suppose. But you can get proteins, you probably know, by eating rice and beans or many other vegetables. But nitrogen is found in proteins. So it's another fairly common one. The rest of these are not as common by mass, and some of them we will talk about as we go through the course, but you don't need to worry at all about remembering those. Just the first 4. Those are the 4 most common elements in living organisms. Isotopes. So isotopes, going back to why is it that hydrogen, hydrogen, I'm going to write it out again here. Remember, I'm going to write it right there. There we go. Hydrogen, it said that the atomic weight was 1.008, and that is because some of them, some hydrogen atoms, let's cross that out, some hydrogen atoms are what we call isotopes. So what's an isotope? Bullet number 1. Atoms of an element may vary in the number of neutrons they have in the nucleus. Bullet number 2. Variant atoms form of an element, variant atomic forms of an element are called isotopes. So if we had a hydrogen atom that had an extra neutron, it would be right here. There it is. You can see in the nucleus, there's 1 proton and 1 neutron. That is deuterium, and it is really rare, and there's an extra neutron there. And that means that this nucleus is a little bit less stable and can be broken apart, say, in a fusion bomb, and a whole lot of energy is released. And that's not a normal chemical reaction. Tritium, tri for 3, right? So that's in hydrogen. 1 proton, and then we have 2 neutrons. 1 proton and 2 neutrons. So these are all isotopes of hydrogen. Let's see. Let's read through these next 2 bullets. For example, all carbon atoms always have 6 protons. That's what makes it carbon. But some kinds of carbon have 6 neutrons. Excuse me. Some kinds of carbon have 6 neutrons, but some are also going to have 8 neutrons. So if you have carbon that has 8 neutrons and not 6 neutrons, then it would be called carbon-14, and that is an isotope of carbon. Carbon-12 is the most common form of this atom. 6 protons, 6 neutrons. Lastly, some isotopes are radioactive and can be used for all kinds of things in research. For example, let's erase this writing here. For example, we can inject radioactive elements into people, and this is like low-level radiation. This isn't going to give somebody cancer. It has a certain amount of carcinogenic risk, but in some areas of research, it is deemed an acceptable level of risk. I wouldn't exactly want to have this done, but sometimes scientists do it. So they inject a person with perhaps a slightly radioactive carbon, slightly radioactive phosphorus that is part of DNA, and they can track all kinds of things by using a camera that can detect that radiation. So here it looks like this radiation that's been injected into this person has concentrated in this area. And so doctors will get various types of knowledge from that because they can see where certain materials are going inside of the person. Another thing that isotopes can be used to do is date things. Carbon, as I said, we have carbon-14. Carbon-14, that's right here. And that is one isotope of carbon. And it can be used to date how old something is. So this picture right here on the right, this is a bone or a fossil, could be used to date either one. Actually, with carbon, it'd be more often used to date a super old bone, like maybe a mammoth that was frozen in the Siberian tundra, and we just dug it up, and it still has some actual bone there that's just been frozen for thousands and thousands of years. Isotopes can be used to date them. So firstly, how is carbon-14 formed? Let me first note that I'm not going to quiz you on exactly how it's formed because it's more of a topic in physics, but you need to have just a basic understanding that it is formed in the atmosphere. So carbon-12, or excuse me, nitrogen-14 basically can get bombarded by these cosmic rays. Those are, let's see, 2 protons and two neutrons that are flying through space, and they come into the upper atmosphere. They run into N14, that's nitrogen, and an atomic reaction happens, and it forms carbon-14. Carbon-14 is not stable. Carbon-14, look up here, it has a half-life that is about 5,700 years. What does a half-life mean? It means if we had 100 carbon-14 atoms, if we waited 5,700 years, then we would only have 50 left. So what this means, let's go back down to this diagram here and look at this last bit here. Carbon-14 can combine with oxygen to form carbon dioxide. That gets taken into plants. Animals will eat the plants, and then the carbon gets integrated into all parts of their body, including their bones, all tissues. And so once this carbon-14 is integrated into their tissues, let's look back up here. let's say, for simple math's sake, that a bone, not a bone, let's say, a woolly mammoth has 100 atoms of carbon-14. It dies. It gets frozen in ice. We dig it up later, and we determine that there are 50 of these atoms remaining. We can then conclude that the mammoth is 5,700 years old. If we found that there was only 25 atoms remaining, then we would say 2 half-lives have occurred. And so then that would be, let's see, 11,400 years old. I will not be quizzing you on this math, merely that isotopes can be used to date things that we dig up. We can date rocks this way as well using other isotopes. So what about electrons? Bullet number 1. The nucleus is stable, but electrons can capture and release energy and form bonds. These 2 points, super critical that you know them. Next, electrons are distributed about the nucleus of an atom in what we call electron shells. So let's take a look at carbon right here. Bullet number 1. The first shell or energy level holds 2 electrons. So let's look at those electrons. 1, 2. Now the first shell is full. No more electrons will fit there in any way. Can't be done. Bullet 2. The second shell and all subsequent shells, at least that are relevant to this course, can hold up to 8. Carbon, again, let's look at how many protons it has. Carbon has 6 protons. So if it is an atom, it's going to have 6 electrons. 6 electrons. So there's 2 in the first shell, and then a remaining 4 in the next shell out. 1, 2, 3, 4. This outer shell is not full, and so carbon can do some reactions. I'll come back to how reactions can or cannot happen. Let's look at oxygen now. Oxygen has 8 protons in its nucleus, so it's also going to have 8 electrons. 1, 2 in the first energy level or shell, and now it's full. 2. Now we have a remaining 6 to put in the next level. Let's count them. And I'm going to get a little bit ahead in the way that I count them, and I'll come back to this a little later. So I'm going to count in a sort of strange way. Watch. 1 electron here, 1 electron here, 1 electron here, and 1 electron here. That's 4. Electrons tend to space themselves out as they fill up an energy level or energy shell. So if we look back at carbon, notice none of the electrons are near each other. And we had 2 in the first level and then a remaining 4. So 1, 2, 3, 4. And none of them are paired up with another electron. So what that means is that carbon can make 4 bonds. Carbon can make 4 bonds. And if you're like, what? I have no idea what you're talking about with this bond stuff. We'll come back to that a little later, but I want to preview right now. If we go back to oxygen now, I have added 6 electrons so far, 2 in the first energy level, and then a remaining 4. We need 2 more. 1, 2. So electrons will then start pairing up after we get to 4 unpaired electrons in the second energy level. So oxygen has got these pairs here. Here's one pair, and here's another pair. These electrons cannot make any bonds. It's kind of like, I don't know, you could think of a long-term relationship. They're not available to meet new people right now, okay? And then these electrons out here, that one, and then the other unpaired one below, this one, they are available for making bonds. So oxygen can form 2 bonds. Okay, now enough for those details. I'm not going to count through all of these as well. You can do so if you want to. Electron shells. Life depends on electrons capturing and releasing energy. Electron shells correspond to energy levels. Bullet number 3 here, energy exciting an atom causes an electron to jump from a lower to a higher energy shell. Let's go look down here. So we have, for example, could be heat energy, could be another kind of energy too, like light energy, or we call that radiant energy. This electron absorbs that energy, and then step 2 over here, it's going to jump to a higher energy level, bang, up to a higher energy level. I think, can I get rid of my video here? I'm going to try. I'm not sure if I'm going to be able to do it though. No, I'd have to stop. So anyway, you can look in your book. This diagram's in your book as well. This electron has gone to a higher energy level. And then number 3, this electron will often release that energy in one of 2 forms. It could be released as heat energy or light energy. And take a look in your book. There's an electron right there. And it is going to drop back down. Let's say that electron's here, they'll drop back down to its original energy level, releasing the heat energy or the light energy as it returns to a lower energy level. Atoms interact. So coming back to bonds, bullet number 1, reactions between atoms depend on the configuration of electrons in the outermost electron shell. This is called the valence shell. So looking at this atom shown right here on the left, let's look at the outermost shell. Let's see, and we'll count the electrons. 1, 2, 3, 4, 5, 6, 7, 8. So that means its outer energy level is full because it can't take any more than 8 electrons. So that means also that this atom cannot form bonds very readily at all. And we also call the outermost level the valence shell, the outermost energy level. Let's look over here. This row here, hydrogen is at the top. Remember, it's got 1 proton. It therefore also has 1 electron. Because it has 1 electron and there's not a second electron in that first energy level, this 1 lone electron will very readily make bonds with other atoms or molecules because this electron is unpaired. Moving over to helium to the right, let's remember the first energy level of an atom can only hold 2 electrons. So helium's got 2 protons. It also has 2 electrons. Those 2 electrons completely fill up its first energy level, making its first energy level full. So helium also does not readily make bonds with other atoms or compounds or molecules. We will come back to these remaining elements later. Atoms interact. Atoms will not react with other atoms if the outermost shell is completely empty or completely full. Such atoms, we can call them inert. That's what I said on the last slide. Example here is neon. I gave you another example on the last slide. 8 electrons are in its outermost shell, so that means it is full. It's not going to react with other atoms. And in fact, all of the elements on the right side of the periodic table are have their outer energy level completely full. Let me go through a quick tutorial of why that is. So hydrogen has 1 proton and then 1 electron. Helium has 2 protons and 2 electrons. That fills up this atom's first energy level. Let's go over to lithium, 3. So if lithium has 3 protons, think 3 electrons also. The first 2 electrons fill up its, if I replaced neon and said, this is lithium now, and I counted 3 electrons, I'd say 1 electron, 2 electrons, and then the third is going to be on the next energy level out, and it's going to be all by itself. So lithium is going to be really happy to interact with other atoms because it has just 1 electron on its outermost energy level. Next, going to the right on the periodic table, Beryllium is going to start adding more electrons. Boron, this is boron, and then this carbon, nitrogen, oxygen, fluorine, and then neon. Each step we take, so from here to here to here to here, we're adding at each step one more electron. So again, if I said this was lithium and then we just start going one step at a time, so let's count the steps. One step, two steps, three steps, four steps, five steps, six steps, seven more electrons. One, two, three, four, five, six, seven, for a total of 8 electrons in that outer shell, and therefore we have neon, which is totally unreactive. Gone a little bit more in depth of explaining why the structure of the periodic table here. So please do pay attention a little more closely to what your book has to say about this stuff. I often get a lot of students asking me why how these electrons are distributed, because the book offers a little less of a detailed explanation, but the book does give you everything you need to know for this course. So all other atoms are reactive other than these ones on the right, and they are wanting to fill up their valence shells. Atoms interact by forming bonds. This table's in your book. I'm not going to read through it, but it's a great way to organize your thoughts on the types of bonds. Bullet 1. Reactive atoms gain stability by electron interactions. Those are called chemical reactions. Some reactive atoms will also gain stability by losing electrons or by gaining them. Either one. They can gain electrons or they can lose them. These interactions create chemical bonds, and we're going to go through two types that are fairly simple, and then the last one not listed here, so this is ionic bonds, and then we're going to talk about covalent bonds. Those are fairly straightforward. The last one is hydrogen bonds. You can see in the table down here, and that'll be the last type of bond that we talk about. So, ionic bonds. Let's look at this fella over here first. On the left, sodium starts with Na. That's its element symbol, sodium. So sodium has, looking down here, 11 protons and then 11 neutrons. We're not too interested in the number of neutrons now because we're talking about the number of electrons, which is often kind of the same as the number of protons. So 11 protons, let's start with the assumption that there must be 11 electrons. So let's count them in sodium. 1, 2 in the first energy level, now it's full. Go to the next energy level. 1, 2, 3, 4, 5, 6, 7, 8. And that's full. So 2 plus 8 is 10. And then 11, that's this last electron on its outermost energy level. So the idea with first the formation of an ion is this. The formation of an ion. If this, let me change color here. Do I want to change color? No, I'm not going to. If this lone electron in the third energy level here, if it was lost, then what would happen is, so let's just pretend it's been lost. It's gone. Now that outer energy level sort of like doesn't exist because it's completely empty. It's completely empty. So now let's consider the second energy level, this one, right? That one has 8 electrons, so it has gained stability. So if there's just one electron in the outermost energy level, it will be lost very readily. And it'll cause very energetic reactions to happen. Okay, so an electron is lost or transferred to another element called chlorine. Now, chlorine, let's skip ahead and just count the number of electrons in its outermost energy level. 1, 2, 3, 4, 5, 6, 7. So 7 is almost 8. If it gains that one electron from sodium, then it'll have a full outer energy level and it gains stability. It gains stability that way. The result is this. Now let's look over here, this whole situation over here. Sodium has lost one electron that has a negative charge, That means now that sodium still has its 11 protons, but only 10 electrons. So that means it's going to have a positive charge of 1. So plus 1 positive charge for sodium. Chloride ion is going to have a negative charge of 1 because it still has its 17 protons, each with a positive charge, and it has gained another electron, so it's got 18 electrons. So that's one more negative than positive, so it's going to have a -1 charge. Most of you probably know that negatives and positives are attracted to each other. Oppositely charged particles are attracted to each other, and this is the formation of an ionic bond. This is the ionic bond, the attraction between a positive and a negative charge. That's an ionic bond. All right. Covalent bonds, a little bit different. Looking at hydrogen, hydrogen basically always forms a bond. There's a little bit of smoke out today. I think it's kind of getting to my throat. Sorry about that. Hydrogen has one electron, and this hydrogen also has one electron, and it's not going to form an ion in this case. It's going to form a covalent bond. Covalent, as in cooperate. They are going to, we can read this little text box here. They're going to share their electrons. So these two electrons are shared between hydrogens, between the two hydrogen atoms. And that means that their outer energy levels are full because they're sharing the electrons. So this hydrogen atom is basically pretending it's got 2 electrons all to itself, so its outer energy level is full. It is more stable, and that is the nature of a covalent bond. This hydrogen atom as well is going to pretend it's got these 2 electrons all to itself, but it's sharing them, obviously. That is a covalent bond. Looking over here, we can see that this carbon atom on the right is sharing one of its electrons with this carbon atom on the left. This is a single covalent bond. Take a look at this symbol down here. So if we have a little line between a C and a C, that means that we would symbolize that as C line C. That means a single covalent bond. A single covalent bond. If we saw 2 lines here, then that would mean that they are sharing 2 electrons. So if this electron was transferred over here, and we said, aha, we're going to put it over there, and this electron was also moved over here, and we put it there, they could share these 2 electrons also, and that would be a double bond, added strength. Practice. So draw the electrons in their correct energy shell. So I apologize if I'm going too slow, but this isn't a chemistry class, and it isn't exactly expected that you know chemistry before. So I kind of like to go over how the structure of an atom is drawn a few times. So I'm going to go over it again. Hopefully you appreciate the extra time. I do know that your time is valuable. So anyway, nitrogen. So what we know here is that there's 7 protons. Oh, sorry, I also meant to do this. If you'd like, please challenge yourself to drawing the nucleus of nitrogen and then adding the electrons in the correct energy levels. You can pause this video now, try to do it on your own. I'm going to now do it for you, though. So if you want to try it on your own, you're going to have to do it now. Because I'm going to start. 7 protons in the nucleus. So that's 7 positively charged particles. Next, I can see the atomic mass is 14 point something something something. I don't need to concern myself with these decimal points because it's basically always 14. There are a few isotopes out there that are heavier than 14, have a little extra neutrons. So 14, that's the mass. So total mass is 14 minus the 7 protons equals 7 neutrons. So there's 7 neutrons. Neutrons have no charge. So I'm going to just draw a little circle around this. We'll call that the nucleus. that is the nucleus, provides stability. The neutrons help keep all those positive charges packed in there. Next, here's one energy level. And then here's another energy level. Okay, now we'll add some electrons. First energy level can carry 1, 2. It's now full. Now let's start adding them to the next. So how many electrons are we going to add? So if there's 7 protons, we're going to add 7 electrons. So 1, 2, 3, 4, 5, 6. Now I'm going to start pairing them up. 7. So let me count again. 1, 2, 3, 4, 5, 6, 7. So there's 7 electrons. That means this is an nitrogen in its atomic form, meaning the number of protons equals the number of electrons. I'm not going to write that out. 7 protons, 7 electrons, and we can predict that this atom is likely going to be pretty willing to form 1, 2, 3 covalent bonds. Say, for example, if we paired them up with hydrogen, so hydrogen, right? That'd be 1 proton, and it's going to have its 1 energy level. Sorry, it's not a very good circle. And it's 1 electron here, and this could form a covalent bond right there. That'd be a covalent bond. And we could do the same thing with the remaining 2 unpaired electrons. I'm going to erase this now and just show you. This is the correctly shows the number of protons and neutrons in the nucleus, as well as the number of electrons that quote unquote orbit around it. 3 of the electrons are unpaired. Atoms interact. Covalent bonds, sharing, covalent, cooperating, sharing those bonds. Cooperating, that's just a mnemonic device. You can remember that's they share and they cooperate. That's how you remember covalent bonding is the sharing of electrons. Okay, most biological molecules contain covalent bonds in some form. So hydrogen, let's go down the list. Hydrogen, capacity of its outer electron shell is 2. Electrons in the shell is just 1. So that means there's a difference of 1 between how many electrons I need to fill its outer shell and how many it actually has. So that means it would like to gain another electron or even lose another electron. So if we're talking about covalent bonds, it's going to share its 1 outer electron with another atom, like maybe another hydrogen atom. Then we'd say, haha, there we go. A covalent bond has been formed. Carbon has 8 in its space for 8 electrons in its outer electron shell, but it only has 4 electrons there. And the first 4 electrons, remember, they're like people. They want their own space, so they space out. Each of those 4 electrons has kind of got their own room, sort of, and so each one of them is willing to form a covalent bond and be shared with another atom. Next, nitrogen. It's just got a few more, one more electron in its outer shell, 5, but it has space for 8, and so it's going to be able to form another 3 bonds to fill up its outermost shell. So then you can look over here. This is just the diagrammatic form. 1, 2, 3 bonds. Covalent bonds are depicted as lines always. One more, and then I'm not going to go over the remaining examples. Oxygen, really common, right? Because it's in water. So 8, it's got space for 8 electrons in its outermost shell. It has 6. Therefore, it's going to want to form 2 covalent bonds. You can see right here, there are space for 2 covalent bonds, like water, H, hey, and another H, H2O, written as H2O. All right. Free radicals, friend or foe. So what a free radical is they are a super reactive. There we go. I knew I had some writing on here. They're super reactive. Free radicals only have a partially full outer shell, so they're super reactive. And for some reason or other, they haven't undergone any kind of chemical reaction to fill their outer shell or to lose enough electrons to make their next lower shell full. Basic idea is they're super reactive, and so you don't want them in you because they can cause basically generalized random reactions. You don't want random reactions happening in the body. Remember that a characteristic of life is that it is organized complexity. You can't have random reactions going on here. Animals have evolved the means of deactivating most free radicals, which is one of the reasons that if you eat natural foods, and what I mean by natural is that they're not processed. For example, it's not an oil that has undergone a chemical reaction like dehydrogenation, hydrogenated, excuse me, a oil that has been hydrogenated. That means it's had a hydrogen added. That's not a naturally occurring type of compound. So if you eat naturally occurring foods such as a vegetable, they also have free radicals in them, but we've, as human beings, have been eating them for so long, we have evolved means, chemical means of deactivating most of those free radicals. Your textbook goes over a case study that you should read. My take on what types of foods should be eaten, should or should not be eaten. Your textbook suggests maybe we should find these molecules that deactivate that deactivate free radicals. Let's find those things. They're called antioxidants, and then we can put them in a pill, and then you can eat them. Problem is if you put those things in a pill, you're introducing a much higher concentration of those things into your body and into the cells. And your cells are, again, organized complexity. And when you throw off concentration gradients that have been that have evolved in cells over thousands and millions of years, you can cause unpredictable chemical reactions to happen. Nutritional science is a science that has a lot to offer, but is often in its infancy. Generalized health advice, something you probably already know. Eat lots of fruits and vegetables because it is what our species has been eating for a long time. Eating meat is fine too, but not only eat meat, probably, and not only sugar and processed vegetables. So several large studies on human populations have also found a correlation between higher consumption of chocolate and a reduced incidence of cardiovascular disease. Think about this. What kind of data is this? You can pause the video and try to answer that. Is this observational data or is this experimental data? You can pause the video. Okay, I assume you might have thought about it. This is going to be observational data because we're just looking at past events, and we didn't actually do an experiment. We didn't take a random group of people, divide them into then two random groups, and have one of them eat a bunch of chocolate and the other one not eat a bunch of chocolate. That would be an experiment. This is simply observational. So it doesn't have the strength of an experimental study, but it still does offer insight because often we can't do experiments on people because people don't like to be experimented upon, and it's unethical to put them at risk. So conclusion: limit intake of highly processed foods. I got a little out of order there. Lots of fruits, lots of vegetables, highly processed food. That means that there's going to be more unknown chemicals in them, and we don't know what kinds of reactions they may have. Now we're going to talk about nonpolar versus polar covalent bonds. We are still talking about covalent bonds, just two types. Bullet 1. Some atoms have a greater attraction. This is called electronegativity. Electronegativity, just the amount of attraction an atom has for electrons, even when they're supposed to be sharing them in a covalent bond. These atoms This is bullet 2 here. These atoms with greater affinity or electronegativity for electrons will pull more strongly on electrons in a covalent bond. So let's look at this example here, and we're just going to say that, switch to a color that's more visible. We'll call this atom A, so just some atom. Then we'll call this atom B. Atom A has a greater electronegativity or attraction to electrons. So what you can see is that this blue field here is showing you where the electrons are more of the time. So the electrons spend more of the time around atom A than they do around atom B. That means that this atom A is going to be having a partial negative charge, and atom B just the opposite, a partial positive charge, because the electrons are spending more time around atom A. Why is it that atom A has a greater electronegativity? Some of you probably will ask that. Others of you will simply ask, what do I need to know to answer the test questions correctly? Well, I explain what you need to know for the test, but to offer you more explanation without getting into physics, atom A here, A, generally we would predict it's got more protons, more P pluses, more protons. Say oxygen, for example. How many does oxygen have? 6 protons, 6 protons. And then maybe if this was hydrogen over here, hydrogen only has 1 proton. So this six positively charged particles in atom A is going to have a more powerful attraction to those negatively charged electrons. All right, so bonding summary. I just went over polar covalent, unequal sharing of electrons. Non-polar covalent, so that means the electrons are equally shared. So the electron cloud, we can kind of think of it, is going to be equally distributed around both atoms. And then back to the first one we talked about, an ion has actually been transferred from one atom to another. So this one got a 1 negative charge, maybe. Sometimes it's 2 negative charges. And then this one's got a 1 positive because it lost an electron. So then there's going to be an attraction between the two because of the opposite charges. And that's the ionic bond. Again, these lectures, if I'm going too fast for you, I strongly recommend that you pause and review what I'm talking about in the book. Non-polar covalent bonds. So, bullet 1. In molecules like H2 or hydrogen, both atoms exert the same pulling force on shared electrons. This type of covalent bond is non-polar, and the molecule is uncharged since both atoms equally share their electrons. 1 positive charge in here, right? Hydrogen has 1 proton, and this one also has 1 proton. So the electrons are pretty equally attracted to both atoms. Polar covalent bonds. Bullet 1. A molecule with polar bonds may be polar overall. That is, different areas of the molecule will have different charges. Example, water. H2O, very important molecule to understand for living things. It is a polar molecule. So what this means is, bullet 1, the slightly positively charged pole is around each hydrogen atom. So the hydrogen is slightly positive. I'll indicate that down here. Slightly positive around this hydrogen atom, and the other hydrogen atom is also slightly positively charged. Why is that? It's because their electrons spend more time around the oxygen over here. The oxygen has 6 protons, right? And so those 6 protons are going to be more effective at attracting these electrons. So there's a slight negative charge around this oxygen right there. So it is polar, kind of like the Earth. There's a North Pole and a South Pole. There is charge. There's a slight negative charge around the oxygen atom and a slight positive charge around the hydrogen atom. If you do not understand what I've just said, pause the video, read through the book. This is a critical idea in this course. Because water molecules form hydrogen bonds with each other, and this results in the many properties of water that make it the most important molecule for life. Hydrogen bonds. Bullet 1. Polar molecules, like water, have partially charged atoms at their ends, so at different ends of the atom. So oxygen is one end of the atom, that's in red in this diagram, and in gray there's a hydrogen atom. Just to clarify what we're talking about when we say one water molecule, this right here is one water molecule. This right here is one water molecule. Now let me erase that. So now you know where the molecules are. Okay, next, because there's a partial positive on all the hydrogens and a partial negative on all the oxygens, these dashed lines here, those are used to represent hydrogen bonds. And they are the attraction between the slightly positively charged hydrogens and the slightly negatively charged oxygens. Notice also that there are many of these bonds. So here's one here. We've labeled a couple more here. All these red dotted lines show hydrogen bonds. So there's lots of them. They are weak, but there are many of them. So altogether, they can have a significant impact on the way this molecule behaves. Water is the key to life. Without water, life as we know it could not exist. Bullet number 2. Why? Because the physical and chemical properties of water help to create the conditions that make life possible. Let's look at some of the properties of water that are so important. Number 1, water molecules are said to be sticky. We say sticky because hydrogen bonds make different molecules of water stick to other molecules of water and other things. If you've ever noticed, water is kind of hard to get off your hands. Once you get wet, this characteristic of wetness, the water stays on your hands. You can even, if you dipped your hand in water, then took your hand out, you might see a droplet of water hanging on the end of your finger. That's because of those hydrogen bonds are attracted to molecules that are part of your skin. This is a property that we call, bullet 2 right here, adhesion. Adhesion means like adhesive tape. Water molecules attracted to other polar substances by H bonds. A part of the skin has some polar molecules in it, and so water can stick to your skin. Cohesion is a different property of water. Water molecules attracted to each other by H bonds. So that means that one molecule of water is attracted to another molecule of water, which is attracted to another, kind of like a bunch of people holding hands in a line or a ring or any configuration. They're attracted to each other, they're bound. But they can also be broken because they're not very strong bonds, right? You can stop holding someone's hand pretty easily. Very briefly, this picture, what happens with trees, which is what enables them to get water from the ground all the way as high as maybe 200, 300, 400 feet up, is that water is literally, water evaporates out the leaves by because light heats up the water molecules up there. So when a water molecule leaves, it is actually able to pull on other water molecules, thus pulling water molecules up the trunk of the tree or the stem of the leaf. And that is because hydrogen bonds. Let's look over here. If this molecule was evaporating out of a leaf, we're just going to have to use our imagination here and think this is in a leaf, and this water molecule is evaporating. It is bound to other molecules of water in the leaf. And so as this water molecule leaves and goes into the air, it pulls on other water molecules, which in turn pull on other molecules of water. pulling water up the stem, up the trunk of the tree, all the way from the roots. Water molecules are sticky. Surface tension, the tendency of water at the surface to resist being broken. So here we can see a paper clip sitting on the top of the water. Here we can see a spider sitting on top of the water, and neither one of them is breaking through the surface because the surface of water is, so if I drew the surface of water here, one molecule of water right here, so that's a water molecule there, it is going to be attracted to the next molecule of water. So there'll be an oxygen and then hydrogen. And it is these bonds, these hydrogen bonds, that make surface tension possible. So this, if I drew a leg of the spider, there's a leg of the spider, okay? And that leg of the spider is pressing down on the surface of the water here, and these hydrogen bonds are preventing the leg of the spider from pressing through. It's not one hydrogen bond, it's millions and billions and I don't know how many a huge number, right? So huge numbers of these hydrogen bonds create surface tension. Water is cohesive. It's attracted to itself. Okay, yeah. Water interacts with many other molecules. So water is an excellent solvent. Solvents, bullet 2 here, solvents are substances that dissolve other materials. The resulting mixture is called a solution. This is what happens when salt is dissolved in water to make a salt water solution. In that example, salt would be called the solute. Water, or H2O, is called the solvent. Solvent. When you put salt in water, it dissolves. You can't see it anymore. That's what we mean. It dissolves, and then we get what's called a solution, a salt water solution. Last bullet here, or almost last one. A wide range of substances dissolve in water to form solutions. For example, shown below are many water molecules dissolving a molecule of sodium chloride, that's salt, in its crystal form. So let's look at this diagram right here, or this part of the diagram right there. So we have a green chloride ion. It's negatively charged. It's a negative ion. And notice these white balls representing hydrogen, they are partially positively charged. They basically surround the chloride ion and prevent it from reforming its bonds with sodium, which is an ionic bond. So water, that is how water dissolves salt. The partial positives of the water molecules surround the chloride ions because chloride's negative. And here, the sodium is is positive, completely one positive charge. You can see the red circles surrounding it. The red circles are oxygen, and they are partially negatively charged. So the partially negative part of water surrounds sodium. Let me remind you, if again I'm going a little too fast here, it is because I'm trying to respect your time. So those of you who I'm not going too fast for, this is suitable for you. And if I am going too fast, you can rewind the video. You can also use the book to augment what I am explaining here. And that's a funny cartoon. You're welcome to read it. Oh boy. Help, I'm dissolving, but bears are insoluble. It's kind of funny. The remainder of the joke down there. Water interacts with many molecules. Bullet 1, water-soluble molecules are hydrophilic. Root words can come in handy here. Hydro means water, and phil means love. Hydrophilic, water-loving. That is, they like to interact with water. Bullet number 2, water molecules are attracted to and can surround ions or polar molecules, thus dissolving them. For example, sugar will also dissolve in water. Amino acids can also dissolve in water. So that's really important. For example, you need to transport sugar around the body in the blood. It's got to be dissolvable in the blood. Otherwise, you'd be trying to transport crystalline sugar in the blood, which would obviously be problematic. Water interacts with many molecules. Bullet 1, water insoluble molecules are hydrophobic. So these don't like to interact with water. Great example is oil, shown on the left here. No matter how much you stir, you're not going to get oil to actually dissolve in water. It is impossible. Water molecules repel and drive together uncharged and nonpolar molecules like fats and oils. The resulting clumping of oil and fats together, that's this last bullet here, the resulting clumping of nonpolar molecules is called hydrophobic interactions. That means that they are both water-fearing molecules. A phobe means a phobia, a fear. So they're both repelled by water. So if you put them in water, different hydrophobic molecules, they clump together because they're all repelled by it. And that'll come back in later chapters to be more important. Water moderates the effects of temperature change as well. So very low or very high temperatures may damage enzymes. Those are molecules in your cells. They may slow down or also speed up important chemical reactions. For example, if you have a fever, that might speed up reactions, which can be dangerous. And obviously, if you get too cold, in this example, that might slow down reactions. If they slow down enough, you can obviously die from hypothermia. So this is why very high fevers can cause brain damage or even death in people, or why when you get too cold, you can also die. Water prevents rapid changes of heat from occurring. So why is that? Water, bullet 1, moderates the effects of temperature change. For example, if you go out on a really hot day, it's 110 out, you walk out the door, you stand there for an hour, your inner body temperature is not going to become 110 degrees. In fact, even if you feel kind of hot, your core body temperature will basically not change. Bullet 2, temperature is basically an indicator of how fast molecules are moving around. Let's now look at these couple of diagrams here. So diagram number 1 in blue, low movement, low temperature. So this diagram is showing molecules not moving that fast. Bullet 2 over here, high movement, that means high temperature. So the red one, it's hotter, red, hot. These molecules are moving faster, and that means that that's a higher temperature. Temperature is simply a measure of how fast molecules are moving. Now the last diagram, 3 over here, you can see enough of it here to get the idea. Remember, water forms lots of hydrogen bonds, which means it's cohesive. It is attracted to itself. So looking at diagram number 1, again in blue, what if these were water molecules? What that means is that we'd be forming all of these hydrogen bonds between them. And so that would mean that it's going to be more difficult for these molecules to move rapidly, because for them to move rapidly, these hydrogen bonds will have to be broken. And that's why you can add energy to water, and the molecules won't move much faster until you really add enough energy to get them moving with enough energy to break those hydrogen bonds. And then you get diagram 2, where they're moving faster. Hydrogen bonds break and then reform, and then break and then reform. The more that's happening, the higher the temperature. So if you have another substance like oil, for example, that doesn't form hydrogen bonds, it will heat up more rapidly. Okay, last bit here. It's a little bit of chemistry. I apologize for that. It requires 1 calorie of energy to raise the temperature of 1 gram of water 1 degree Celsius. That's what we call specific heat. How many calories of energy are required to raise something 1 degree Celsius if we have 1 gram of it. So 1 calorie of energy is a lot of energy for 1 gram. I'm going to make up another example. Let's just say canola oil. Canola oil. To raise the temperature of canola oil, 1 gram of it, 1 degree Celsius, we could say it's maybe just going to be 0.2 calories. I'm sorry, 2 calories of energy instead of 1 calorie. So water 5 times more. That's a lot of energy to cause the water to increase in temperature. Okay, water requires a lot of energy to turn from liquid into a gas. That's called the heat of vaporization. For example, when water in your sweat evaporates from your skin, it carries with it energy from its surroundings, i.e. your body, maybe the air too, which makes your skin and body cooler. Let's go through this graph over here. I'm going to start down here at A. So look at the bottom left-hand corner where I'm drawing here, right about here. A, ice. So as you start adding energy, so this is energy added on the x-axis, the ice eventually goes up in temperature until it gets to 0 degrees. At that point, notice we can add more energy, but the temperature on the y-axis does not go up, as shown right here by this flat line. It's not going up. It's not going up at all. And that's because we're slowly breaking hydrogen bonds. And once we've broken enough of them by adding more and more energy, the ice will melt. Now we have liquid water. We keep adding energy, so going right on the x-axis, we keep adding energy, and the temperature also keeps going up. And then we get to about 100 degrees. That's the boiling point of water in Celsius. At this point, notice we keep adding energy. We go really far on the x-axis, and the temperature does not change. It just stays flat here. This whole section of the graph here, this here is flat. And that is because what's going on there is the hydrogen bonds in water are being broken. So eventually, if we add more energy, then we'll break enough hydrogen bonds and the water begins to boil. Some of the water molecules escape into the gas phase, forming steam. Now, if this was the case, if we are looking at sweating in a person, somebody sweats, that means that there's water on the surface of their skin. And that the temperature of that water is not going to be 100 because you don't want boiling water on your skin, right? So this is a little bit of abstract thinking here. So consider that water on your skin, and as it evaporates, what molecules are evaporating? Which molecules are becoming a gas? The molecules that happen to just sort of randomly absorb a bit more energy from your body and get enough energy to break their hydrogen bond and become a gas, and they float off. And they take that energy with them. The energy that came from your body as heat to break their hydrogen bonds is carried away with that molecule into the air. Another really clear example here is just somebody sunbathing. Because the human body is mostly water, a sunbather can absorb a lot of heat energy without sending his or her body temperature soaring. Water forms an unusual solid, ice. Why is it unusual? Because ice floats in liquid water. Usually the solid form of something is more dense than the liquid form, but ice is just the opposite. Ponds and lakes freeze from the top down and never freeze completely to the bottom. I mean, at least if they're deep enough. And that enables a lot of plants and fish to survive over the course of a winter in really cold climates. What is going on here? Why is ice less dense than liquid water? This right here, you don't need to memorize any of the details of the structure of ice, but how bonds form in ice between different water molecules just cause it to be less dense. The water molecules are spaced out more. You can kind of see that they're spaced out more. Let me see if I can get a so here there's just kind of empty space there between these water molecules. And that's just because that's how the bonds orient themselves. This isn't a class in chemistry, I promise. So that's the extent to which we need to understand. There's all this empty space in between the water molecules in ice, so it is less dense and therefore floats on water. The left side of this diagram here, this is showing liquid water. This here, sorry, there you go. That is liquid water. So the molecules of water are more dense there. All right, just about at the end. Acidic, basic, and neutral solutions. In a normal sample of water, a small fraction of water molecules will break apart into ions at any given time. Pure water contains equal concentrations of H plus and OH minus. This right here, this is OH minus. It's an ion. It's a negatively charged ion. We can see right here, negatively charged. And this is hydrogen. It is positively charged. This double arrow symbol here means this reaction is reversible. So this is constantly going both from water to hydroxide ions and H pluses, and then going in the opposite direction as well. So what that means is the hydroxide ion can combine with H pluses to form water. So this is a reversible reaction. Acids, bases, neutral solutions. Solutions where H pluses are in greater concentration to OH minus are said to be acidic. So if there's more H plus than OH minus, it's an acid. Any substance that releases H pluses when they're dissolved in water, we call those acids. Hydrochloric acid is one of the stronger acids around. You put it in water and it breaks apart or dissociates into H plus and Cl minus. H plus adds what we call sort of the acidic component of a solution. H plus. More H plus means more acidic. Carbon dioxide in water forms carbonic acid, which releases H plus. So therefore, carbon dioxide becomes a kind of acid in water, carbonic acid. Solutions where OH minus is greater than H plus are called basic. Any substance that binds up H pluses or releases OH minus when dissolved in water is said to be a base. So even if it isn't adding OH minuses, if it's reducing the amount of H pluses, then it's going to make the solution comparatively abundant in OH minus because it's reducing the amount of H plus. So we'd still call it a basic compound or a basic compound if it's somehow binding up those H pluses because it's at least making it less acidic. Sodium hydroxide ionizes in water, also called NaOH, sodium hydroxide, and it becomes Na plus and OH minus. More OH minus means more basic. Here are a couple of examples of basic solutions or basic compounds. Baking soda, chlorine, bleach, super strong, and also ammonia. It's a table of some of the things that are more and less basic and neutral and acidic. Starting with really low pHs, this is just an indication of whether or not it's acidic or basic. Stomach acid is very very acidic, and things that we eat are also fairly acidic as well. Even fruits and vegetables and beer, of course, is acidic. All that carbon dioxide carbonation forms carbonic acid, so it's acidic. Coffee, still a little bit acidic, less than 7. When we get to 7, we call that neutral. That is the concentration of H plus equals the concentration of OH minus. That would be pure water. Then lastly, everything to the right is increasingly basic, with the most basic thing we have all the way down here, drain cleaner. Keep out of reach of children. It's not a fun compound. Okay, buffers maintain constant pH. What is a buffer? Well, a buffer is a compound that accepts or releases H plus in response to pH change. So it accepts or releases H plus in response to pH change. So that means that if you're adding acids to something, if there's already a base in it, you are adding H plus. There's an H plus, and this buffer is just gobbling it up. It's binding those H pluses. So the addition of H plus is essentially canceled out. The bicarbonate buffer found in our bloodstream prevents pH change. So bicarbonate, it's a buffer. It's going to bind up and actually release, in other situations, H+. Last bullet, the job of buffers is to keep a solution basically the same, a constant pH. Your blood must remain within a very set range of pH or all kinds of problems will occur. Carbon dioxide, we probably know that we breathe out carbon dioxide, and that means carbon dioxide is coming out of us. It's essentially coming out of our lungs, and it gets into the lungs from the blood where there's lots of water. So cells that produce carbon dioxide as a waste product, they are immediately releasing carbon dioxide into their watery environment. And that is going to reversibly form the carbonic acid. Carbonic acid, remember, so it says that it's an acid, and what acids do is they release H pluses. So they release H pluses, and then these H pluses will be absorbed by the bicarbonate ion, and that will keep them keep H pluses from increasing to too high of a concentration gradient. You're not going to be asked to explain how this buffer works. This is simply an example. You just need to know that pH buffers prevent pH changes by binding or releasing H+. All right, I went a little bit long there, but remember class time would generally be even longer than this, so we're still being a little bit more efficient. I'll see you next time.